All right, let's jump right into this explainer. Today, we're unpacking the fascinating and honestly, somewhat hidden journey of your internet data when you fire up a commercial VPN. We hear the term VPN thrown around constantly, usually marketed as this ultimate impenetrable privacy shield. But today, we're looking under the hood. We're going to break down the exact mechanics, the routing decisions, and the encryption layers that actually make this technology tick. We all kind of view it as this magic privacy button, right? You click a little toggle on your laptop, it turns green, and bam, you feel totally invisible. But what really happens when you click connect? Well, today, we're acting as digital detectives. We're going to track the exact path of a single internet request, byte by byte, to see if that magic button is actually keeping you as safe as you think it is. So here's our flight itinerary for today. We'll start with the VPN magic button, move on to leaving the local network, trace the encrypted undersea journey, hit the decryption checkpoint, look at fooling the destination, and wrap up by comparing the top providers. Okay, part one, the VPN magic button. Let's get this journey set up. Let's ground this all with a real-world example. Imagine a guy named Arjun. He's sitting at home in India, and he really wants to watch a show that's only available on the US Netflix catalog. Crucially, he wants to do this without his local internet service provider snooping on his web traffic. So Arjun opens up his ProtonVPN app, picks a US server, and types in netflix.com. To him, this feels completely normal. But behind the glass of his screen, that one simple action just triggered a massive sequence of unseen events. Moving to part two, leaving the local network and the OS routing decision. The second he hits connect, we enter stage two. The VPN app, using some incredibly powerful underlying protocols like WireGuard, literally hijacks his device's default routing behavior. Normally, your default route just blindly sends absolutely everything out to your local home router, but a VPN creates a virtual interface. It changes the rule to a total lockdown. Every single bit of data is now forced through the encrypted VPN tunnel. Absolutely no exceptions. Now, there is a catch here, and it's a big one. It's called a DNS leak. Basically, a DNS leak happens when your device asks for the IP address of a website, and that request accidentally slips outside the encrypted tunnel, going straight to your local ISP. If that happens, all your encryption effort goes straight down the drain because your ISP still gets a neat little list of every website you're visiting. To prevent this, the VPN absolutely has to override Arjun's DNS settings. This ensures his request for Netflix.com is handled entirely by ProtonVPN's own servers. His Indian ISP stays totally in the dark. Part 3. The encrypted undersea journey. Let's go from the app to the ocean. So how does this build into an international data transit? In stage 3, Arjun's device does a quick digital handshake with the ProtonVPN US server to exchange encryption keys. His HTTPS request asking for Netflix is then encrypted. But here's the really clever part. That encrypted data is then wrapped inside a brand new outer packet. It's kind of like putting a locked metal box inside a plain, regular shipping envelope. The outside envelope only shows his real home IP as the source and ProtonVPN's US server as the destination. Now the packet hits the public internet for stage 4, traveling all the way from India, across undersea backbone cables to the US. Let's use some X-ray vision here for a second. What does Arjun's ISP actually see as this data leaves his house? Honestly, almost nothing. They see an encrypted connection to a random US IP address. They can see roughly how much data is moving and when it's moving, but absolutely zero details about Netflix. The content is completely hidden. That outer envelope is literally all they get. Which brings us to part 4, the decryption checkpoint, the stage 5 reveal. Here is where we hit a massive plot twist. That traveling data packet finally reaches the VPN server in the United States. And the ProtonVPN server receives the packet, verifies Arjun's session, and actually decrypts that outer layer. So at this exact moment, ProtonVPN's server can see in plain text that this request is going to Netflix. Just think about that for a second. This is the single point in the entire journey where his traffic is both decrypted and not yet at its final destination, which means the VPN provider itself has total, unhindered visibility right at this checkpoint. Part 5, fooling the destination. Let's look at NAT and forwarding. So what happens at stage 6? Well, the server just saw everything, so it has to quickly cover its tracks to fool the final destination. The VPN server takes Arjun's decrypted request and uses something called NAT, Network Address Translation. Essentially, it rips off Arjun's real Indian IP address from the return label, slaps its own US IP address on there instead, and then forwards the request directly to Netflix. And that brings us to stage 7, Netflix's viewpoint. Netflix gets the request and just assumes it's a completely normal US user connecting from a standard US data center or residential IP. Because it sees that US address, it happily serves up the US content catalog. As far as Netflix is concerned, Arjun is just some guy chilling in Ohio. They have zero visibility into his real identity, his actual location in India, or his original ISP. They package the video, send it back to the ProtonVPN server, which encrypts it again and sends it back to Arjun. The deception is totally flawless. Finally, part 6, comparing the top providers. Because now we really have to ask, who do we trust? Because the VPN server absolutely must decrypt the traffic to forward it, we have to ask who we're trusting with that incredible level of visibility. When we objectively compare the top providers based on the source data, it's really fascinating to see how they handle the heavy lifting. ExpressVPN uses their custom lightweight protocol alongside WireGuard. NordVPN uses NordLynx, which is a heavily modified version of WireGuard. And ProtonVPN relies on standard WireGuard or their own custom stealth protocol. But notice the common thread here. They all maintain independently audited no-logs claims, and they heavily leverage privacy-friendly jurisdictions, places like the British Virgin Islands, Panama, and Switzerland. But how do they actually mitigate that massive stage 5 risk, that moment of plain text vulnerability? If the server sees your real IP and your destination, how do they protect you from themselves? ExpressVPN leans heavily on their audited RAM-only server infrastructure. NordVPN takes a really cool approach. NordLynx actually assigns a dynamic local IP per session, completely double-natting the connection, so it's incredibly hard to correlate a user to their IP, even internally. And ProtonVPN offers Secure Core, which completely routes traffic through multiple Proton-owned servers in privacy-friendly countries before it ever exits to the internet. No single server ever sees both your real IP and your final destination. At the end of the day, going through the mechanics in this explainer brings us to a pretty profound realization. A VPN doesn't magically eliminate the need for trust on the internet. It simply shifts it. It takes the trust you were previously forced to give to your local internet provider, and it transfers it to a centralized server halfway across the globe. You've seen the encryption, the clever routing, and that exact vulnerable moment of decryption. The tech works beautifully to hide you from your ISP and the website you're visiting, but it leaves you with one final, unavoidable question. Who do you trust more?